So far we have seen that power method works. Power method gives us the dominant eigenvalue and the corresponding eigenvector of a square diagonalizable matrix A. We still don't know that how it works. So in this lecture we will briefly discuss the theory behind power method. We will show that for any vector x, I should be able to write Ax as Aj, Avj summed over j equals 1 to n, where v is the eigenvector of this n by n matrix A. And then if lambda 1 is the dominant eigenvalue, we will see that the unit eigenvector v1 will be given by a to the power kx divided by norm of a to the power kx as k tends to infinity. Recall our discussion on power method that finds the eigenvalue and eigenvector of matrix A, which is diagonalizable n by n matrix. Since this matrix is diagonalizable, the eigenvectors v1, v2, etc. up to vn, they are linearly independent. Since these vectors are linearly independent to each other in an n-dimensional space, we can use these vectors as basis vector. Therefore, any n-dimensional vector x, if I take, that x can be uniquely described as a linear combination of these eigenvectors v's. So x is essentially a sum of aj, vj, where j goes from 1 to n and a1, a2 all the way up to an are scalars and unique for this x. Also, I know that avj equals lambda j vj, since vj and lambda j are the eigenvector eigenvalue pair for the matrix A. Now I can write Ax equals Aj, Avj. This is simply coming from the fact that x equals sum Aj, Vj. So if I multiply A both sides, then I have Ax equals sum Aj, Avj. Aj is simply a scalar, and Aj, Avj is summed over j equals 1 to n. Now we know that Avj is equal to lambda j vj, so I can write lambda j vj here. So Ax equals Aj lambda j vj, which is summed over j equals 1 to n. Now once again I multiply both sides by a, so I have a square x on left hand side, and right side both a and lambda are simply scalar, so I have Avj. Once again we see that Avj is equal to lambda vj, so this equation comes as Aj lambda j square vj summed over j equals 1 to n. We can now clearly see the emergence of a pattern here. When I have Ax, I have Aj lambda j vj, and then when I have a square x, I have Aj lambda j square vj. So we can now generalize this as a to the power kx equals Aj lambda j to the power k vj, and this is summed over j equals 1 to n. Now this crucial step. Here I take this lambda 1 to the power k out of the summation sign. Therefore inside the summation I have lambda j to the power k divided by lambda 1 to the power k Aj vj summed over j equals 1 to n. Taking out of this lambda 1 to the power k out of the summation sign is not arbitrary. Here lambda 1 is special. This is the dominant eigenvalue, such that absolute lambda 1 is greater than absolute lambda I, where I goes from 2 to n, which means absolute lambda 1 is greater than absolute value of any other eigenvalue. Therefore, if I take this ratio lambda j to the power k divided by lambda 1 to the power k, for large value of k, such as k tends to infinity, I reach delta 1j. Delta 1j is Kronecker delta, but if you don't know about Kronecker delta, don't worry about it. It simply means that delta 1j equals 1 for j equals 1. Otherwise, delta 1j is 0. We can see clearly why is that. If j equals 1, then of course lambda 1 to the power k divided by lambda 1 to the power k is 1 no matter what is the value of k. However, if j is not equal to 1, we know that lambda 1 is the largest eigenvalue. Therefore, lambda j by lambda 1, we hope that it will be less than 1 in its absolute value. So when I keep on multiplying this less than 1 value, eventually for large enough multiplication, that means for large enough k, we go toward 0, which means for j not equal to 1, this ratio will be 0. Now we come back to this equation once again, and I set limit k tends to infinity both sides of this equation. So limit k tends to infinity a to the power kx equals limit k tends to infinity lambda 1k summation j equals 1 to n lambda j to the power k lambda 1 to the power k aj vj. And then we know that the only term that will survive here is when j equals 1, and at that point this ratio is simply 1, which means in this entire summation only j equals 1 term has something, everything else should be 0, which means that this becomes lambda 1 to the power k, and here everything is 1, only j equal to 1 survives, so that means a1 v1. With this idea of limit k tends to infinity a to the power kx is equal to limit k tends to infinity lambda 1 to the power k a1 v1, I take norm both sides, and now I have limit k tends to infinity norm of a to the power kx equals limit k tends to infinity. This lambda and a are simply scalar, so they come out of norm, and I have norm of v1. So now if I divide a to the power kx by its norm and I allow k to go infinity, I have this limit k tends to infinity lambda 1 to the power k a1 v1 divided by same lambda 1 to the power k a1 and norm of v1, which means I have here this v1 divided by norm of v1 on right hand side, and this is simply the unit vector v1. So this is simply the v hat 1, which is equal to k tends to infinity a to the power kx divided by norm of a to the power kx. So it clearly tells us that if I take an arbitrary vector x and I do this multiplication a to the power kx, then for large enough k, this a to the power kx divided by the norm of a to the power kx will be an unit vector, that is the eigenvector corresponds to lambda 1, which is the largest eigenvalue of matrix A. This is exactly what we were doing in power iteration. So this analysis proves the algorithm of power iteration. Now you have all the understanding of power iteration. You should be able to write a pseudocode of power iteration. You can read this pseudocode and try to improve it further. Here I have started from an initial guess which is not equal to 0, and I have set an arbitrary value of error. Then I'll continue with updated value of this v, and I'll continue with finding the error u minus v and a norm of that. Once I'm happy with the eigenvector, I can find the eigenvalue very easily. Now that we understand the power method as well as how it's work, and also we have seen the inverse power method, you can write a computer program to find the eigenvalues and eigenvectors of this matrix A. You have to use power method as well as the inverse power method, and I hope now you understand both the power and inverse power method well enough to write this computer program. That's all for today's lecture. Thank you, and I'll see you in next class.